Hello guys, this is the seventh problem from our TIFR series. We've already solved six problems before. This is the seventh problem and it is from the molecular spectroscopy chapter, and it's telling us a beam of hydrogen molecules travel in the z direction with the kinetic energy. The molecules are in excited state from which they decay and dissociate into two hydrogen atoms. So one molecule gives us two atoms, and the final velocity is perpendicular to the z direction, so its kinetic energy is always 0.8 electron volt. The energy released in this dissociative reaction is what? So to find the energy released, right? Now this is to solve. Before solving this problem, there is an experiment that you should know, and it's called Compton scattering. It's in the modern physics chapter before, I think, the wave nature of particles. This accounts for the particle nature, where you hit a heavy nucleus with a electron or a charged particle with a velocity, and then apply momentum conservation and energy conservation to find the energy of the scattered molecule, right? And yeah, this is the theory that we need to apply here, because okay, let us first draw to simplify the problem. That is, we have an H2 molecule here. This is dissociating, it's not hitting something, it's just dissociating after a time. So this is an H here, this is another H here. This is the perpendicular z-axis that they have said. Let this be theta, right? One of the particles is perpendicular to the direction, not both. Sorry for this thing. So again, like, reading the question is very important here. I have to do step by step. So let us this be 90 degree red cap, and yeah, this is another H molecule. So the advantage of having a 90-degree angle here is that when you break it into components, the sine 60 and cos 60 will be easily dissolved into the problem. Now, so for the first thing that we need to do is apply momentum conservation. This is exactly the way we solved Compton scattering. If you don't know the theory, just check it in Wikipedia or write it in the comments. I would explain in a video. And so momentum conservation first we do for the H2 molecule, that is pH2 is equals to root 2 m into k. K is the kinetic energy, right? And so what they have said in the problem, it is 1 electron volt. So this will become 4 into mp. Okay, but mp is the mass of proton, because there are two molecules, so two protons, and so 4 mp. Now we have to do linear momentum of each atom which is moving perpendicular, that is this one, right? This one we need to find momentum. So we can say pH, oh sorry, this is looking like a pH factor. So pH perpendicular like this, that is equals to It will be, it is again root 2 mp into k. It is one proton, one electron, so we can take it one proton atoms, so that is equals to, so what is the okay, 0.8, right, is the question. 0.8 electron volt. This is the perpendicular z direction. It has a kinetic energy. Okay, this kinetic energy is given, it is 1.6 mp. Now for the other each atom we have a theta component, so let us break it. This is the momentum. This is p2 cos theta. This is p2 sin theta. We are taking this as momentum p2, energy e2, this as momentum p1, energy e1, just to simplify the problem. And yeah, this we got the h perpendicular or something. Let us just make it p1, that's easier. Now p2 is what, p2 will be, okay, so p2 cos theta, like that we write. p2 cos theta is equals to p, I will tell you why. And p2 sin theta is equals to p1, right? Now what is p? Okay, one thing that I did mistake here, just I replace the theta on this side. You can take theta on whichever side you want. It's just the way we do it is really, this should be the p2 cos theta, this should be p2 sin theta. I change the coordinates anyway. So p2 sin theta, you see, it's just in the opposite direction in which the p1 has gone, right? So p2, so and on this axis for momentum conservation, p2 sin theta has to be equals to the p1 momentum, and p2 cos theta is in the direction of h2, right? So for this momentum to be conserved, so p2 cos theta has to be the momentum of our initial h2 molecule. So p2 cos theta should be equals to p. This is the first condition, this is the second condition. Why we are doing this? Because in a reaction we know the two things, the two physical quantities that always will be constant is momentum and energy. So that is the basis of quantum mechanics and higher physics. Everywhere this is the only two constant quantities that we have in physics, like in the laws of physics. So we have to apply like that. So at this point is our dissociation point, right? This is our dissociation point, say dp. So you can also take it like as an origin. So in this dissociation point, the momentum and the conservation of energy has to be applied. So what will be the energy if at this dissociation point, or what will be the momentum at this dissociation point? It will be 0, because this is conserved, right? Now from this dissociation point, multiple particles are scattering on many sides from one molecule or number of molecules. So you need a specific point from where everything starts. That's how you will conserve things like that. p2 cos theta is equals to, see, in this direction p2 cos theta, and p is also in this direction of h2 molecule. Again, for p2 sin theta to be conserved, this at this point, say dp, so whatever magnitude of the vector at any point p2 sin theta, that should be equal to the p1 of the perpendicular h molecule, like that. Now let us proceed to the next step. So what we do here is square and add. square and add both the equations. So you will get p2 sin square theta plus p2 cos square theta. Sin square theta plus cos square theta is 1. So p2 is equals to, this is p1 square plus p, and this is whole root for p2. Now we know p and p1, which is given. So what was our 4 mp, right? p1 square 4 into mass of proton. Let us just check what was our p1. It was 4 into mp. So pH2 square will be 4 mp, and our p square will be 1.6 mp mass of proton. Root, this is root 5.6 mp. Now kinetic energy, that is equals to p square by 2m, and p is, this is necessarily the kinetic energy of the p2 molecule. So p2 square, we have root 5.6, p square is 5.6 mass of proton by 2 into mass of proton. These two are cancelled. This is 2.8 electron volts. Now we have to find the dissociative energy. Dissociative energy is the energy of the energy difference between product minus reactant. The energy lost after forming the product with the energy of the molecule, right? Because when the molecule is bursting, there is some energy. Obviously some particles will have energy. Suppose you burn a firecracker, so the energy that is you put into it, that will burst into giving out some particles, but some energy will be lost in light and sound also. So that is the dissociative energy. So like that you have so this is the kinetic energy of p2, that is 2.8. We are already given that the perpendicular hydrogen atom is moving with 0.8, and our reaction has 1 ev energy, so that is 1, which will give you 2.6 ev. And let's check the option. This is our correct option. So the video is getting too long, so let us conclude here. If you have any doubt, put it up in the comment section. Thank you for watching. We'll meet soon with the next problem. Thank you.